There are few directors as iconic as Quentin Tarantino. If you're about to view one of his films, you probably have some expectations. Guns, blood, gritty characters, dialogue, and, of course, a lot of fucks.
Any of you f***ing pricks move, and I'll execute every motherfucking last one of you!
Tarantino's dialogue is perhaps the most iconic part of his films. His very first movie, Reservoir Dogs, was ostensibly about a jewel heist, but it mostly involves post-heist dialogue between the surviving crew taking place in a fairly nondescript warehouse.
The cops didn't show up until after Mr. Blanc started shooting everybody.
As soon as I heard the alarm, I saw the cops.
Man, I'm telling you, it wasn't that soon, okay?
In other films, the quantity of profanity really varies with the intensity of the current scene. That is, when things get heated, the fucks come out. But in films like Reservoir Dogs, the fucks seem ubiquitous and even spread throughout uniformly in the dialogue. In this video series, we'll consider different ways to model the distribution of fucks in the movie Reservoir Dogs. But first, let's take a look at the data. I downloaded the film's script from the Internet Movie Script Database, or imsdb.com, so all of the following analysis is based on that specific text, which seems to be pretty close to what you see in the movie. In that text, there are nearly 13,000 words of dialogue, with 200 of them being fuck or fuck derivatives, such as the classic fucking or motherfucker, or less standard derivatives such as hardy fucking har and any fucking where. We can treat this as a discrete time counting process. In this video, we will use the non-homogeneous Poisson process in discrete time to model these fucks. So a Poisson process is a type of stochastic process with a multitude of applications. The idea is that we watch something over a period of time and count the number of occurrences or events that happen throughout that period of time. A typical example is watching patrons arrive at a bank. When the bank is open, the patrons arrive at, say, a rate of one customer every 15 minutes, on average. And such a model can help a bank decide how many tellers to have available. So this would be an example of a homogeneous Poisson process. It assumes that the arrival rate is constant throughout the day or the time period of the observed process. But in actuality, the rate will vary quite a lot at the bank. For example, in the morning, business may be slow. It might be, say, one customer every 30 minutes. But at the end of the day, when people are coming home from work and need to stop by the bank very quickly, the rate may jump up to, say, one customer every 5 minutes, on average. Of course, this is all on average. This latter case is what we would call a non-homogeneous Poisson process, because it's a Poisson process, but the rate varies as we move through time. The question I want to know is, how homogeneous are the fucks in Reservoir Dogs? Strictly speaking, the Poisson process assumes independent increments, which would imply that the number of fucks in two disjoint time intervals do not depend on one another. So for this data set, the assumption is not strictly valid, at least within a movie scene. But when cutting from one scene to the next, it is reasonable to assume that the fuck counts are independent. We first fit an homogeneous Poisson process to this data, which merely returns a rate parameter of 1.5 fucks per 100 words, which is exactly the fuck frequency in the script. Note that the rate is an average. In any time interval, we may see more or fewer fucks than expected. More interestingly, we can use stepwise variable selection via the NH Poisson package in R to fit a polynomial model to the non-homogeneous rate parameter. So what does that actually mean? Well, that means we're going to try to model the rate of fucks throughout the script, and the result is a degree 4 polynomial estimating this change in the rate of fucks throughout the script. We can overlay now a moving average smooth version of the process and compare the model to the smooth stochastic process. In this case, we notice that the rate is fairly constant throughout the script, but it does seem to drop a little bit around 80% of the way through the film, before then spiking for the exciting and tense ending scenes. No spoilers here, don't worry. We can further use the likelihood ratio test to compare the homogeneous model to the non-homogeneous model. And what we find is significant evidence in favor of the non-homogeneous model, indicating that Quentin Tarantino's use of is not completely homogeneous throughout the script. To contrast this with other words, we can consider two more extreme cases. By replacing the word with the word what, we see what an homogeneous Poisson process may look like. While there are certainly little local fluctuations, the homogeneous model fits the data just as well as the non-homogeneous model. Taking an Occam's razor approach, we prefer this simpler model being the homogeneous one, as it has fewer parameters in it. In the opposite extreme, if we want to replace the word with the word Joe,
this ain't a goddamn city council meeting, you know.
We have a highly non-homogeneous process. This is because Joe, the crime boss, who is one of the only characters in the film to have a real name, appears in some scenes and is a topic of conversation in others, but then is completely absent from other scenes. So in conclusion, the in Reservoir Dog are more homogeneous than some words like Joe, but still less homogeneous than others like what. In the next video, we're going to consider other ways to model the in Reservoir Dogs, so make sure to stay tuned for that.